Sampling distribution of the sample mean. For the purposes of statistical inference, a single sample is usually taken from a population, and appropriate statistics are computed from the sample. However, there are many different samples that can be formed, and the statistics computed from these samples may vary in value. Thus, we may regard each particular statistic as a random variable whose range of values are the values of the statistic that can be computed from each possible sample. The probability distribution of a sample statistic is called sampling distribution. Now let's have an example of this sampling distribution of the sample mean. 5 small bags are known to contain 5, 8, 10, 6, and 4 marbles in each bag. These bags are placed in a box and 2 bags are drawn from the box. Construct a sampling distribution of the average number of marbles in a bag. Solution: we will treat the 5 bags as our population. Our samples consist of all possible combinations of 2 bags, each that can be drawn from the box. That is what we call the population. So the 5 bags are the population. Now there are combination of 5 taken 2 or 5 factorial divided by 2 factorial, 5 minus 2 factorial, which is equal to 120 over 12, which is equal to 10 possible samples, and the average number of marbles in each sample can be computed. So let X denote the number of marbles in a bag, and let small letter x denote any values of X. Also, let this symbol denote the average number of marbles in each sample of size 2, because we are actually drawing 2 bags. The results are shown below. So sample size 2, so the combinations are bags with 4 and 5 marbles, bags with 4 and 6 marbles, 4 and 8, 4 and 10, 5 and 6 marbles, up to 8 and 10 marbles. So there are 10 possible samples or 10 possible combinations. Now, getting the average or the mean, we have 4 plus 5 divided by 2, 4.5. 4 plus 6 divided by 5, 4 and 8, 6. We have 4 and 10, 7. 5 plus 6 divided by 2, 5.5, and so on and so forth, up to 8 and 10, that is 8 plus 10 divided by 2, which is 9. Now, it can be seen from the table that the sample mean varies from one sample to another. So if you are going to get this sample, for example, you got 4 and 5, the mean is 4.5. If you get 4 and 8, the mean is 6. So the sample mean varies from one sample to another. Since random sampling is used, the 10 samples have equal chances of being selected. Thus, we can regard the sample mean as a random variable. Its probability distribution, the sampling distribution of the sample mean, is shown below. So this one here. So all the possible mean, we have 4.5, 5, up to 9. Now, as you can see, there's only one 4.5, so 1 out of 10. There's only one 5, so 1 out of 10. Now, as you can see here, for 7, there are 2 7s. This one, 6 and 8, and then 4 and 10. No? The mean is 7. So there are 2 7s. So 2 out of 10, or 1 over 5. So this is what we call the sampling distribution of the sample mean. Since the sample mean can be treated as a random variable and its sampling distribution can be determined or computed, it is possible to compute the mean, variance, and standard deviation of the sample mean. The standard deviation of the sample mean is also known as the standard error of the sample mean. So standard deviation is also called the standard error. The standard error represents the average deviation of the sample mean from the population mean. The smaller this error is, the better is the estimate provided by the sample statistic from the population. In this case, sample mean. From the population parameter, since the sample mean is guaranteed that will not deviate much from the true population mean. Let's have example number 2. Find the mean, variance, and standard deviation or standard error of the sampling distribution of the mean given in the preceding example. So, as we all notice, this one, 4.5 plus 5 and so on, the probability is 1 over 10, 1 over 10, 1 over 10. Now, adding all that, the common factor is 1 over 10. And then for 7, the probability is 2 over 10. Now, simplifying that, that will be 6.6, and that is the sample mean or the mean of this sampling distribution. Now, for the variance, we have this formula. Variance is equal to this minus this one. No? We know that the mean is 6.6 already, so we set aside the mean. And then we have this mean squared, so we square every mean. And then the probability is still the same, 1 over 10. And then for 7 is 2 over 10. Take note that 7 will become 7 squared. Now, simplifying that, we have 45.3. Using the formula, 45.3, that will be this one, minus the mean squared. So 6.6 is squared. Computing for that, we have 1.774. So that will be our variance, 1.74. For the standard deviation or standard error, we will be getting the square root of the variance. So the variance is 1.74. Getting the square root of that, square root of the variance, 1.74 square root is 1.32. So this will be our standard deviation or standard error. Now, the random variable x represents the number of marbles. Earlier, we had the mean. This time, the number of marbles as our random variable. Now, the mean and the variance of the number of the random variable x are computed below. So the probability is 1 over 5 because there are 5 bags. 4 marbles for the first bag, 5 marbles for the second, 6 marbles for the third, 8 for the fourth, and 10 for the fifth bag. So 1/5 is the probability for each bag. Now, getting the mean or expected value, as you can see, 1/5 plus this one, the answer is 6.6. So as you know this, the mean of the sample distribution is 6.6 also, which is the same as the mean of this random variable that represents the number of marbles. So they are the same. Number of marbles, the mean of that is the same as the mean of the sampling distribution. Now, for this one, in order to get the variance, so we'll have this formula, squaring the mean, squaring the number of marbles, 4 squared plus 5 squared plus 6 squared and so on. And then multiplying that by 1 over 5, we have 48.2. Using the formula of the variance, 48.2 minus the mean squared, minus 6.6 squared, that will be 4.64. Now, as you can see, the variance of this random variable is not the same as the variance earlier, which is 1.74. But they are related by this formula. So the variance of the sampling distribution is equal to the variance of the number of marbles over n, and the sample number of samples, which in this case we have 2 because we'll be getting 2 bags out of 5, and this n 5 because there are 5 bags as our population, so n minus n, small letter n, over n minus 1. So this will be the relation or the formula related to variance of x, the number of marbles, and the sampling distribution. The variances of x are related by the formula, this one again. We show this equation using the given example. So 1.74 as our sampling variance of the sampling distribution, and then 4.64 as the variance of the random variable number of marbles. So over 2 because there are 2 bags for the sample, 5 minus 2, 5 because there are 5 bags, divided by 5 minus 1. Now as you can see, 1.74 is equal to 1.72. So that's how related the variances of x, number of marbles, and the sampling distribution are. If the sampling is done with replacement or sampling from an infinite population, the variances are related by the equation, this one. So the variance of the sampling distribution is equal to the variance of the random variable, in our case, number of marbles, over the number of, or the sample size. If the sampling is done without replacement, or sampling is made from a finite population of size n, the variances are related by the equation, this one. Now the factor n minus n over n minus 1 in the equation is called the finite population factor, or FPC. When the sample size n is very small, FPC is almost 1 and may be ignored.